अब इसमें अपन यहाँ पर वो जो ब्रोशर जो था ना, उसको अपन इसकी स्क्रीन पे डाल देते हैं 1 मिनट में।
अच्छा,
है ना? तो वो दिखता
खोल के
रहेगा।
रखेंगे।
हाँ, अपन ऑन करके रख देंगे। 11 o'clock तक वो चलता रहेगा। फिर जब चाहेंगे तो वो जो भी अपने को करना है। तो अब विट्टी जी यूट्यूब पे पब्लिकली शुरू कर दिया। अब इसमें टाइम लगेगा ना, ब्रोशर जो थी
थोड़ा सा लैग आ रहा है ना, पहले
तो
बोल
लैग
चुके हैं।
आता है।
दूसरे खोल लूं? अच्छा, अपन जूम पे भी देख रहे हैं इसको। तो यूट्यूब वाले को बंद कर दें क्या?
हाँ, ठीक है। अब इसमें शेयर स्क्रीन है ना, ब्रोशर ब्रोशर स्क्रीन। मेरी
क्या नाम से था हमें ब्रोशर? ये वाला है ना? अब ये वाली विंडो को कर देंगे अंकल बोल रहे हैं। वो फिर से कर लेते हैं।
और अपन एक काम करते हैं,
वीडियो को ऑफ कर देते हैं उतनी देर के लिए।
ऑडियो
दूसरा वाला वो इंटरनेट से चला रहे हैं ना पूरा?
वीडियो सही हो जाएगा। वीडियो और ऑडियो दोनों को
यही से होगा ना?
नहीं, ये तो यूट्यूब पे आ रहा है।
अच्छा अच्छा, उधर है उधर है, वो टैब खुला है।
पार्टिसिपेंट पूरे यूट्यूब में आएंगे और पैनलिस्ट जो हमने जो बोलने वाले हैं
ऑन करूंगा तो फिर
हेलो, हेलो सर, इज इट ऑडिबल?
हाँ सर। हाँ सर, ऑडिबल है।
ऑडिबल है ना?
हाँ सर।
ओके सर, ओके।
हेलो। अच्छा, एक बात और देख लें अपन, जैसे जो बोल रहे हैं वो अपने आप स्क्रीन में आ जाएगा कि कैसे?
वो तो आना ही चाहिए।
एक साथ पैनल के पूरे मेंबर भी दिखते हैं।
हेलो।
हाँ सोनू,
हाँ हाँ
आवाज आ रही है?
हाँ, आ रही है।
ऑडिबल है ना?
ऑडिबल है, ठीक है।
ओके।
वीडियो कहाँ से दिखेगा? वीडियो
वीडियो तुम्हारा?
हम्म,
हाँ, एक मिनट।
उनका वीडियो चालू नहीं होगा।
तुम्हारा वीडियो चालू नहीं होगा, देखो तुम्हारा वीडियो चालू नहीं होगा, देखो। हाँ, वीडियो ऑन हुआ। हाँ, ओके, ठीक। किसका?
हम दिख रहे हैं क्या?
हाँ, दिख रहे हो?
हम दिख रहे हैं? हमको तो नहीं
हाँ हाँ,
दिख रहे।
दिख रहे हो। हाँ,
हम तो अपने आप को नहीं दिख रहे हैं।
ये
लैगिंग बार-बार रोटेट हो रहा है।
ये यूट्यूब चल रहा है, दोनों चल रहा है, इसलिए हो रहा है कि
और सुनिए ना, हमको हमको अपना ऑडियो बंद करना होगा तो, सिर्फ सुनना होगा तो।
उसी में होगा ना, देखो ऑप्शन, स्क्रीन में टच करो। अपनी स्क्रीन में टच करो।
हाँ हाँ, जिसमें आप लोग का ब्रोशर दिख रहा है।
हाँ,
अच्छा, आपको रीनेम करके विकास तो देख सकता हूँ, लिख दूं क्या?
क्या?
ऐसा तो कुछ नहीं दिख रहा कि ऑडियो स्टॉप करना है।
अरे ये ऑडियो और वीडियो जो है, यहाँ से मैं म्यूट कर दूं क्या?
म्यूट कर देंगे ना, म्यूट है ऑप्शन। हेलो।
आप टॉक करके देखो ना, मतलब वो फुल स्क्रीन में आएगा कि नहीं आएगा, आपका स्टॉप शेयर करना पड़ेगा अपने को, हालांकि
ये तो आ रहा है।
जैसे आप बोलोगे तो फुल स्क्रीन में होता है, वैसा नहीं होता क्या इसमें?
फुल स्क्रीन
वो आपको
ये यहाँ
ये
से,
जो पैनल है ना,
नहीं वो ये स्पीकर व्यू में जाने से आ जाएगा फुल स्क्रीन।
सोनू,
जो भी
हाँ,
बोलेगा
हाँ,
ना उसका फुल
मैं
स्क्रीन
म्यूट
आएगा।
करके देख रही हूँ, आ रही क्या आवाज बताना, ठीक है?
हाँ, नहीं म्यूट कर रही हूँ।
म्यूट हो गई ना, वो देखो।
हाँ, म्यूट हो गए। अच्छा, वही
वही
अनम्यूट कर
वही के
सकते।
पास है।
ओके,
वीडियो भी अपना कोई वही कर सकता है, तो वो हम करेगा।
मेरा भी है।
नहीं आप अटेंडेंस में हो।
हाँ,
हेलो।
हाँ
हाँ, हम इससे बाहर निकल जाते, फिर 11 बजे ऑन करूंगी, है ना?
हाँ, 5 मिनट
अभी
पहले
बंद
ऑन कर
कर
लेना।
दूं?
हाँ, अभी बंद कर दो।
हाँ ठीक है ना, ओके
ठीक
चलिए।
है,
ये लैपटॉप
टेस्टिंग
है
डन।
ना, उसमें चार्जिंग
मोबाइल है, मोबाइल नहीं, वो चार्ज है 100%।
चलिए, पूजा कर लेती हूँ, फिर लगाती हूँ।
ओके ठीक।
हेलो
विकास सर,
हाँ सर।
शेड्यूल के हिसाब से
जी
पहले एक वेलकम स्पीच हो जाएगा।
जी
पहले एक वेलकम स्पीच हो जाएगा,
हाँ सर।
उसके बाद रामाराव सर का इनवाइट करते उनका स्पीच हो जाएगा।
हाँ
फिर मैं फिर रिक्वेस्ट करूंगा नेहा मैम से कि वो पूरा डिटेल में डॉक्टर प्रोफेसर डर्क कोलमैन के बारे में बताए।
ठीक सर।
फिर मैम खुद हैंड ओवर करेंगी स्पीच की कि मेरे को फिर बोलना पड़ेगा?
नहीं, वो खुद हैंड ओवर कर देंगे।
ठीक है ठीक है। फिर उनका जैसे स्पीच हो जाएगा फिर इनका डिस्क्रिप्शन आ जाएगा
हाँ
KVR मूर्ति जी का।
ठीक।
इनका डिस्क्रिप्शन मेरे को ही देना है?
नहीं, वो दे देंगे, नेहा दे देगी।
अच्छा, इसमें नहीं लिखा है, ठीक है।
हाँ।
ओके। इनके बाद उनका स्पीच होगा, फिर
सुदीप्ता सोम।
इनका भी नेहा मैम ही देंगी
हाँ सर।
डिस्क्रिप्शन।
हाँ, उसके बाद फिर आपके पास आ जाएगी माइक।
ओके। फिर कंडक्शन ऑफ द प्रोग्राम लास्ट में, हाँ ठीक है, ये शेड्यूल बताना है कि आज क्या क्या हुआ है। फाइनली जगजीत मैम को देना है वो कंक्लूड करने के लिए।
हाँ सर।
ठीक सर, ठीक सर, मैं ऑनलाइन रहूंगा ऐसे ही।
जी
ठीक सर।
ख्वाजा सर,
ख्वाजा सर।
सर
आप जो है ना आपके चेहरे पर फोकस करने से ऐसी लग रही
सर मैं सीटिंग चेंज कर रहा हूँ सर।
है। हाँ वही बोल रहा हूँ।
कॉन्फ्रेंस हॉल में जा रहा हूँ, एडमिन कॉन्फ्रेंस हॉल में।
और सुना ना, तो रामाराव सर का
सर
हमारा सर को मैं बोल चुका हूँ कि सर जिसमें बात करेंगे
उसी
सर
इसमें करो।
उसी उसमें
जैसा
दोनों आमने सामने बैठे हैं। हाँ।
कौन से काम है?
चार्जर उधर है।
यूट्यूब में देखो ना दीदी, यूट्यूब में आ रहा है क्या? यूट्यूब में क्या दिख रहा है? मैं पेस्ट करूं क्या इस यूट्यूब पे स्ट्रीमिंग लिंक? आपके पास नहीं है? एक मिनट, ग्रुप में आया होगा। नहीं, उनके यहाँ सब अर्ली मॉर्निंग है, अभी 6 बजा होगा। पौने 8 बजे तो वो चालू करेंगे, मतलब 11:15, मतलब उनके लिए 7:45 है। ये आ रहा है जूम। हाँ यूट्यूब। हाँ पहले बिट्टी और देशमुख सर का, अब जो भी चलेगा आ गया है। फोटो शेयर शेयर यूट्यूब में। इसको भी शेयर कहाँ कर सकते हैं?
टाइटल तो दिख रहा है।
दिख रहा है?
दिख रहा है?
हाँ
फोटो भी है ना?
नहीं,
सिंह सर का नाम
इंटरनेशनल। ये एक बार चेक करना पड़ेगा, बिल्कुल बोलिए ना।
तो मैंने पार्टिसिपेट
हाँ कोई एक ये
मैं
बोल के
मैंने
देखिए।
पार्टिसिपेट
जी मैडम, एक बार आप बोल के देखिए, टेस्टिंग हो जाए थोड़ा सा।
नहीं, यूट्यूब वाला बोल नहीं सकता।
नहीं नहीं, आप बोलिए तो वो सुनाई देना चाहिए। पार्टिसिपेंट बोलने से नहीं।
अच्छा
आप लोग
तो
हो जाएगा, हो जाएगा, हो जाएगा।
ऐसा तो हो गया। मेरा कहाँ है?
मैडम को लिखा है, मैडम को कर दीजिए।
नहीं नहीं मत कर, वो लोग देख रहे होंगे, रहने दे। रहने दे ना, क्या फर्क पड़ेगा? ये हम लोग को
ऑन है।
विकास सर,
हाँ सर।
अभी ऑडिबल है?
हाँ सर।
आरके सर स्क्रीन अभी ओके है?
हाँ नहीं स्क्रीन तो हाँ
स्क्रीन
आपका
ओके है,
दिख
आपका
रहा
चेहरा
है।
दिख रहा है।
अभी ठीक है सर?
हाँ थोड़ा और फोकस कर लो सर। हाँ सर ठीक है।
ठीक है ना?
हाँ सर। हाँ सर जी।
जी सर।
जूम लिंक का मत करना।
हेलो
हाँ हाँ उसका करना, क्योंकि सब वो फिर आएंगे ना तो फिर वो अपना ऑडियो और वो म्यूट नहीं कर, क्योंकि उन्हीं के पास अथॉरिटी है, हम लोग नहीं कर सकते, है ना, तो प्रॉब्लम होगी। तो जो यूट्यूब वाला लिंक है वो सब शेयर कर दो कि वो 10:55 को ज्वाइन कर लेंगे। तो यूट्यूब में, हाँ हाँ यूट्यूब में सारा लाइव स्ट्रीमिंग चलेगा, कोई प्रॉब्लम नहीं है, ठीक है। और अपने लोग जो है वो जूम में ज्वाइन कर सकते हैं, कोई प्रॉब्लम नहीं है, ठीक है। लेकिन आप, हाँ हाँ लेकिन आप क्या बोलते हैं वो उसमें ऑडियो और वीडियो को म्यूट ही रखना, ठीक है। इको होगा नहीं तो इको स्टार्ट हो जाएगा सर, ठीक है। हाँ बस 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 ठीक है।
सर अपने कॉलेज फैकल्टी को
हाँ
सर्कुलेट हो गया सर गूगल लिंक?
हाँ सर हो गया है।
ग्रुप में तो डाले हैं, आप एक बार चेक कर लो ना सर।
ग्रुप में नहीं डला है सर?
सलूजा मैम क्या?
मैं डालूं क्या?
डाल रहे हो क्या सर?
आपके पास आ गया तो आप ही शेयर कर दो।
हाँ मेरे पास है, डाल दूं?
आप ही शेयर कर दो सर।
जूम लिंक शेयर नहीं करना है सर।
अच्छा शेयर नहीं करना है?
नहीं यूट्यूब लिंक शेयर करो।
समझ नहीं आया सर।
यूट्यूब का लिंक शेयर करो सर, जूम का करेंगे ना
हाँ
तो अपने लिए, अपने जो पार्टिसिपेंट मतलब अपने जो लोग हैं उन्हीं लोगों को अपन जूम से शेयर करेंगे, है ना।
ओके ओके
बाकी
सर,
लोगों
समझ
के
गया।
साथ प्रॉब्लम ये होगी कि उन लोग अपना माइक और वीडियो म्यूट नहीं करेंगे तो इको जनरेट होगा।
ओके सर ओके।
सर मैं ग्रुप में डाला ना चेक कर।
अमित सर भी है साथ में, मनीष सर भी है साथ में।
जी
सर
सर
मैं
जी।
ग्रुप में किया हूं,
ये किस पे ऐड किया? हाँ, सामने ही हुआ है सर।
हाँ एडमिट
कर
कराना
देता
है।
हूँ।
अभी कितने लोग हैं हम लोग इसमें? मेरा भी नहीं आ रहा ना?
नहीं आपका नहीं आ रहा
अजय सिंह के बदले में मेरा आ रहा होगा।
मेरे को लग रहा है मैडम का भी है ना, नाम चेंज करें एक बार करके।
तो रीनेम हो जाएगा।
नहीं होस्ट में नहीं बदलेगा ना, सब कुछ उसी का है करके।
अच्छा नहीं बदलेगा।
वही खरीदा है ना तो उसी को ऑथराइज किया है। कोई बात नहीं ना, जब वहां मैं आऊंगी तब तो मैं ही रहूंगी ना।
म्यूट ऑन करिए।
All allow participants to mute themselves. नहीं, current and new participant will be muted.
हाँ ठीक है, जो करेंट मतलब चलता रहेगा वो।
हाँ
हाँ ठीक है, तो सारे लोग को यस काफी है। अब बोलो।
होस्ट पर से हेलो लिंक सेंड मी बोलते हैं भाई रुकले सर।
इनका थोड़ी है।
नहीं है फिर इंटरेस्टेड इंटरेस्टेड
क्या बोल रहा है?
देख क्या हो रहा है।
चल अपन इसको इस तरफ सेट कर लेते हैं।
वो चार्जर
ये है बस, हटा दीजिए।
टर्न कर लो। मैम यहाँ पे
चालू है।
चार्ज यूट्यूब भेज दो क्या भेज देता हूँ। जूम वाला ठीक है पूछो। परसों है? देखो पोस्ट कितने कर रहे हैं वो सब तो मैम
उनके
आप
सवाल
कनेक्ट
है।
नहीं, आप कनेक्ट नहीं हुए क्या? अच्छा
मेरा
इसी में
अजय
तो
सिंह
देखो।
के नाम से है ना।
ठीक।
ये तो व्यक्ति वाला नाम है।
देखो ख्वाजा सर कनेक्ट हो गए है ना, आप भी कनेक्ट हो गए।
ये सब मिला है ना।
हाँ हाँ सर।
ये मिश्रा सर। हाँ सर। जानते हैं?
सर म्यूट है।
और क्या? विकास को तो
नहीं
मिश्रा सर को नहीं है।
सर कल बोलेंगे, मैं परसों बोलूँगा।
कल मौसम बना रखा
हाँ
है।
नहीं
शाम
कल
को
शाम को 5:30 बजे। नहीं परसों 4:30 बजे से। हाँ सर।
क्या हो रहा है? ये जो है ना
होस्ट,
हाँ, होस्ट का ऑडियो चलना
तो होस्ट का ऑडियो
गुड मॉर्निंग भाई।
हेलो, गुड मॉर्निंग सर।
गुड मॉर्निंग, गुड मॉर्निंग, गुड मॉर्निंग, गुड मॉर्निंग, गुड मॉर्निंग।
गुड मॉर्निंग। कैसे हैं?
बिल्कुल ठीक। आपके कॉन्फ्रेंस में लिमिटेड है ना?
हाँ एकदम।
एकदम घर की कॉन्फ्रेंस है ना?
घर की कॉन्फ्रेंस।
अरे तो मास्क तो उतार दो, यहाँ पे क्या कौन आने वाला है आपको वायरस देने के लिए? आपका चेहरा, अरे इंटरनेशनल है।
इफेक्ट ऑफ कोविड है सर।
अरे कोई इफेक्ट नहीं है, तुम तो अभी एक रूम में 2-3 ही लोग होंगे ना।
अभी तो
कॉलेज कॉलेज से बात कर रहे हैं ना?
बाकी लोग यूट्यूब में आएंगे सर। नहीं, घर में।
घर में ही है क्या? वाह वाह वाह, फिर घर में भी मास्क लगाते हो?
हाँ, ये बैठे हैं ना आजू बाजू में। सोशल डिस्टेंसिंग।
हाँ, कितना टाइम है और?
सर 11 बजे से स्टार्ट करेंगे।
अच्छा, आधा घंटा टाइम है। चलो फिर आधे घंटे बाद मिलता हूँ।
जी सर।
ओके,
ओके सर, ओके,
बाय बाय।
हेलो विकास सर,
हाँ सर। हेलो।
हाँ विकास सर,
हाँ सर, आवाज आ रही मेरी?
हाँ आ रही है। मेरी क्लियर आ रही है आपको?
हाँ सर, एकदम क्लियर है। डेक ऐड हो गए।
Yes, I'm fine. Good morning.
सर, हाउ आर यू सर?
I'm fine, thank you.
देखिए,
उनको तो हमारी स्क्रीन दिखती है।
हाँ सर को दिख LSI एग्जीक्यूटिव कमेटी फॉर पीरियड हो गया। नहीं नहीं नहीं, वो सर ने भेजा है, लिस्ट आ गई उनका, देखा देखा। म्यूट फिर क्यों ना? नहीं।
सर गुड मॉर्निंग सर, रामाराव सर।
आज कैसे कीमत में नहीं बना।
हेलो
सर गुड मॉर्निंग सर।
गुड मॉर्निंग, केवीआर मूर्ति।
गुड मॉर्निंग सर।
विकास बोलो, चालू हो गया?
सर 5 मिनट में होने वाला है सर स्टार्ट।
अच्छा, ఫస్ట్ హూ స్టార్ట్? నమస్తే రామారావు గారు, ఎలా ఉన్నారు?
బాగున్నారా మీరు కూడా?
యా గుడ్.
యా మీటింగ్ ఆఫ్టర్ లాంగ్ టైం.
యా షూర్.
वो नहीं, वो वाला फोन नहीं है क्या? हेडफोन ठीक है, चलो। ख्वाजा सर, आई एम ऑडिबल?
Yes sir, audible sir. The voice is somewhat less sir.
Voice is less, okay. Where is the audio?
Sir, keep the microphone nearby sir.
This one, now it is okay?
Yes sir, somewhat audible sir.
Some more nearer to your mouth.
Yeah. Now it is okay?
Yes sir, yes sir.
Yeah, okay.
अभी आ रहा है सर।
ठीक है। यही कर दीजिए।
हेलो,
एक ले लो और उन लोग को भी एक दे के चाय दे दो सबको।
Good morning, Neha madam.
प्रणाम सर। ओम साई राम।
Sairam. How are you?
आई एम फाइन सर।
Good. Drink is also.
सर माय वॉइस इज क्लियर और आई हैव टू यूज हेडफोन।
आपकी वॉइस जो है ना कट रही है बीच बीच में, हेडफोन यूज कर लीजिए तो ज्यादा अच्छा रहेगा।
ओके सर, 1 मिनट।
पुलीमैन, पहिलमैन।
कौन जुड़ा है? ड्रिप जुड़ गए हैं। कृष्णा, विकास दुबे, अमित ठाकुर, बहुत कम लोग जुड़े अभी तो। क्यों? अभी तो बहुत कम ही लोग जुड़े हैं। क्यों, क्या ऐड है? इतने लोग हैं? ओके।
लाइव यूट्यूब में
Vikas sir, how many people will join this? Hello, Vikas sir. विकास सर।
हाँ सर।
कितने लोग ज्वाइन होंगे इसमें अभी?
सर बता रहे 2 मिनट में सर।
सर यूट्यूब में ज्वाइन होंगे सर।
अच्छा, यूट्यूब में यहाँ पे सिर्फ इतने ही दिखेंगे क्या जो दिख रहा है ऊपर?
जी सर। यहाँ सर जो होस्ट है सर वही दिखेंगे।
अच्छा, बाकी सब यूट्यूब से देखेंगे।
जी सर।
ओके, राइट, गुड, ठीक। सो जब चालू करना रहेगा बताइएगा, मैं भी इसको म्यूट करके रखा हूँ।
जी सर, जी जी। हेलो।
Vikas sir, shall we start the session?
Yes sir.
A very good morning to all of you, and a warm welcome to the speakers for today's program, International Webinar Series, June 2020, in association with Luminance Society of India, in collaboration with Government YYT PG Autonomous College, Durg, Chhattisgarh, and also Bela Institute of Technology, Raipur. So the today webinar is on worldwide effect of COVID-19 on research and development. So concerned to this webinar, I once again heartily welcome to all of you for this webinar series initiated by Department of Physics. So before proceeding ahead, I request Principal, Bela Institute of Technology, Raipur, Dr. T. Ramarao sir, to please bless us for the successful organizing and completion of the program. Sir, please. Sir, it's not audible, sir. Not audible, sir.
not okay. Amit sir को बोला not audible. Amit sir audible नहीं है अभी सर. नहीं.
Hello.
No audible. Yes sir.
Yes sir.
Hello.
Yes sir, audible sir.
No, it is audible. Okay.
I once again request Principal BIT Raipur to bless us in hosting this program of worldwide effect of COVID-19 on research and development. Sir, please.
Yeah, I'm sorry. I welcome everybody in this 3-day international webinar series on worldwide effect of COVID-19 on research and development. It is starting today, 24th, and it will end on 26th. This is jointly organized by, as Khwaja sir has told, Department of Physics, Government, Vishwanath Yadav Tamaskar, PG Autonomous College Durg, and Birla Institute of Technology, Raipur, in association with Luminescence Society of India. The motto behind organizing this webinar is to explore the current scenario of research and development in the various parts of the world by exploring the various possibilities and new ventures. The webinar also aims to provide a common platform to all researchers, academicians, and industry professionals worldwide to share their views in context with the current pandemic situation. Under the difficult circumstances, it is only through advanced research that world shall be able to fight the pandemic. I heartily thank our speakers to agree to share their views with us on these new dimensions of research and development in these pandemic times. Following are the speakers for this webinar. So we are very happy that again, Dr. Polman from Belgium is joining us. Martha from Poland is also joining us. On 24/6, we have Dirk Polman, Professor, University of Ghent, Belgium. Professor KVR Murthy, Professor, MS University, Baroda, also President, Luminescence Society of India. Today's third talk will be Sudipta Som, National Taiwan University, Taipei. And tomorrow's, that is second day, 25th June, the first speaker will be Dr. K. Ramanujacharya. He is professor in Rowan University, New Jersey. And Dr. Subhas, he is also professor, Rowan University, New Jersey. And the third speaker, Madam Martha from Poland. Day third, that is 26 June, Dr. Dhananjay Kumar Deshmukh, Chobu University, Japan. Dr. S.G. Doble, Professor, RTM University, Nagpur. Total, these are the speakers who will participate in this webinar. They will give their views in this topic. And total participants, those who are registered for this event, this webinar, are 640 approximately. In this webinar, it is very good to see that there are international participants. Participations is also there. That is from Taiwan, South Africa, South Korea, Japan, Belgium, and some Asian and European countries. And as far as our India is concerned, that is many states are also participating. Participants from many states are also there. especially Maharashtra, UP, Bihar, Noida, Delhi, Madhya Pradesh, Karnataka, Andhra Pradesh, Tamil Nadu, Telangana, Kerala, Chhattisgarh, Odisha, Jammu Kashmir, Gujarat, Punjab, Chandigarh. It means almost across all the India, the number of participants are there to listen this webinar, different speakers. And this is again a great opportunity for us that we had one international conference here where number of speakers, number of scientists who have participated in that activity, in that international conference, are also participating in this webinar. So I welcome everybody, and in behalf of Government PG College, Durg, and Bhilai Institute of Technology Management, I welcome you all, sir. And I congratulate the organizer from both the colleges for a great event, and I give them the best wishes for a good and beautiful webinar, and best of luck to everybody. Thank you to the organizers. Thanks a lot.
Thank you so much, sir. Thank you for your blessings in initiating this program. Giving the overall overview of the program, today we are having 3 speakers. Professor Dirk Polman, full professor, Ghent University, Belgium. Professor KVR Murthy and Dr. Sudipta Som. So before going ahead, I request Dr. Neha Dubey to give a brief description about Professor Dirk Polman. Ma'am, please.
Can you hear me, sir?
Yes, ma'am, you are audible.
Yeah, you are audible. Please.
Thanks, sir. Thank you, sir. First of all, I would like to good morning to all the speakers and all the scientists and participants and faculties all over the worldwide. Our first talk is of Professor Dirk Polman. So I would like to invite Professor Dirk Polman, University of Ghent, Belgium. Before starting this talk, I want to say something or give a brief introduction of Professor Dirk Polman. He is a very famous personality in the field of research and highly energetic person. He had completed his PhD in 1994 from the University of Ghent. He joined Department of Solid State Science as an assistant professor in the same university in 2001. Become associate professor in 2009, and from 2012 onward, he is working as a full professor in the Ghent University, Belgium. He has been published more than 200 articles in the Wave Science and Scopus, nearly 54 articles in last 5 years. Professor Dirk Polman has guided 33 master's students and 13 PhD theses. Presently, he is serving as an associate editor in the renowned Journal of Luminescence and Material, MDPI. Area of research is piezoelectric transaction memory device, NIR, medical imaging, luminescence, and so other areas. So now I would like to invite Professor Dirk Polman. Please, sir.
So thank you very much for your kind introduction. Also, thank you very much for inviting me to be present at this event. And I still have very fond memories of my real visit to Raipur just a few months ago. This seems like a very, very long time ago, since we could freely travel and meet each other. And now everything is virtual, so it's really a different world. But I'm really happy to be back, and so to share some ideas with you. You will see that my presentation is only partly related to COVID-19, but at least I have tried to incorporate some ideas on COVID-19 and make a relation between luminescent materials and viruses. So maybe I can try to share my screen for the presentation. Can you see the presentation in full screen?
Yes, sir.
Okay, that's fine. Shall I start presentation or should I wait?
Yeah, you can start, sir.
Okay, thank you. So the title I have given to this talk is Traps in Phosphorus from Virus Preservation to Geological Dating. I will be treating a number of different materials, but in fact, I will try to show that all these different materials and different applications finally come down to a single set of physical phenomena. And in reality, all these materials come down to the same principle. So you all know luminescent materials. So if we have a luminescent star and we illuminate it with an UV light, then the star starts to shine. If we stop the illumination, then the star also stops shining. And this we call photoluminescence. Now there's a different physical phenomenon where even if we switch off the flashlight, the UV flashlight, that the star still keeps giving off light, which means we have persistent luminescence. So this star can keep giving off light for many minutes or even hours. Now, this kind of materials has a lot of applications, mainly in the field of safety illumination. So we can show exit signs, we can show emergency situations. Also in toys, these materials are used. Even there are some special applications, like in Canada, people made a $2 coin with persistent luminescent materials. Also, one can buy baby soothers with some glow-in-the-dark material, so with some persistent luminescent material, which means that these materials are really safe. Otherwise, it's not allowed to use this for baby soother. Long time ago, radioactive materials were used to enhance the luminescence of persistent luminescent materials. But nowadays, these materials are perfectly safe, which means that they can be used for a very large range of applications. Also, it's possible by using different compounds that different emission colors can be achieved. The most common material for persistent luminescence is strontium aluminate doped with europium and dysprosium, and this we can see on the top row. And this is really the workhorse of persistent luminescence, since the luminescence can last for really many hours. And also the eye is very sensitive for green light, so it's really an ideal persistent luminescent material. But other colors can also be achieved by using different combinations of hosts, so the material where the dopants are incorporated, and different dopants, like in case of strontium aluminate, europium, and dysprosium. Now, what is essential in persistent luminescence is that there are traps in the material. Not this kind of traps, like for wolves or for mice or whatever, but traps for charges. So here, very basically, on the bottom part of the figure, or of the slide, we can see the basic principle of persistent luminescence. So when light is incident on the material, then dopant ions can be excited to an excited state. And when electrons move back to the ground state, light is emitted. This we call photoluminescence. But it's also possible that charges are transferred from this excited state to a trap level. And this kind of trap level, where we see some examples here, these trap levels can store the energy for a very long time. So it's possible that the light is not emitted directly, but that the energy is stored in these traps, and then very slowly, by thermal excitation, these traps are emptied and light can be emitted in a delayed way. And so if these traps can store the energy for minutes or for hours, then also the emission, so the very slow detrapping of the trap levels and then the recombination can also last for many hours. The way that these trap levels are emptied is by the available thermal energy. So if at room temperature, then there's not much thermal energy, and then very slowly these traps are emptied. If we heat up the material, then we are doing thermoluminescence. Then the traps are emptied faster, and we have brighter but shorter persistent luminescence. Now, in case we want to use these materials, for example, for road markings, we have a problem in wintertime. Maybe not in Raipur, but in Belgium, it gets cold in wintertime. And then there's not enough thermal energy to liberate these traps from the charges from these traps and to achieve persistent luminescence. In the same way, the device would work during summertime. So the persistent luminescence phenomenon is highly temperature dependent. And so the rest of my talk will mainly be involved with looking at the temperature dependence of the persistent luminescence of a material. So basic principle, we have trap levels with a different depth, and depending on the depth of these trap levels, the temperature needed to liberate charges from these traps is different. A shallow trap, there the temperature can be low, or the decay will be relatively fast. For a deep trap, the probability that at room temperature the charges are liberated is very low. So we need a higher temperature, or it will take a very long time to liberate these charges. Now we can try to study the temperature dependence of the persistent luminescence by performing so-called afterglow measurements. So measuring the light intensity as a function of time at different temperatures. And we can choose a whole range of temperatures. These are not actual measurements, these are simulations. And so in this way, look how long is the decay, how bright is the decay, and what is the total amount of light we can emit from the persistent phosphor at different temperatures. Now you can imagine this is only shown for 2 hours, but in fact we should measure this for longer time. This takes a very long time. So this is not a very interesting way for studying these persistent phosphors because it takes a lot of time. And we will try to devise a way to study this in a more efficient way. And this is the procedure we followed for making these measurements. So charging, the charging phase we see here, charging is just illuminating the persistent phosphor. And we can illuminate this persistent phosphor at different ambient temperatures. This can be room temperature, but this can also be lower or higher temperature. Then, in some cases, we apply a certain time of fading. Fading means that we don't heat the material, we just keep it at constant temperature, and we look at how the decay of the emission changes. And then we perform a thermoluminescence measurement. Thermoluminescent measurement means that we continuously increase the temperature and we follow the emission as a function of time or as a function of temperature. Now, this is the kind of measurements we achieve. Now, this is a quite complicated figure, but I will try to explain as well as possible. These are all measurements on the benchmark phosphor strontium aluminate with europium and dysprosium, so the well-known green-emitting phosphor. On the top left here, we see thermoluminescence measurement. So we increase the temperature and we look at the light emission when we have charged the phosphor at minus 60 degrees centigrade. So we have here shown in blue, we have charged the material, so illuminate the material at low temperature, and then we have made the thermoluminescence measurements, and we can see that around 100 degrees centigrade light is emitted. Now, if we don't immediately make this thermoluminescence measurement, but if we wait for 30 minutes, so we observe a fading time of 30 minutes, then we almost get exactly the same thermoluminescence measurement, which means that at minus 60 degrees, during these 30 minutes waiting time, no light is emitted, because the thermoluminescence measurement and the area under this curve gives an idea of how much light is emitted upon heating the material. But waiting does not make any difference. So at minus 60 degrees, we don't have any light emission. It's too cold, and there's not enough thermal energy to liberate these charges from the persistent phosphor. So this also means that we cannot use strontium aluminate with europium and dysprosium at this low temperature. And then we make the same measurements at higher and higher temperature. We can see minus 40 degrees. There's a little bit of light emission when we wait for 30 minutes at minus 40 degrees, because there's a little bit of difference between the two curves, the thermoluminescence measurements without waiting and with waiting. And we can see the higher the temperature, the higher the difference between these two curves. Because, for example, here, this is, for us, it's room temperature, 20 degrees centigrade. There's a big difference between the thermoluminescence measurements without waiting and with 30 minutes waiting. And so the area, the difference between these two curves gives an idea about how much light is emitted during half an hour at 20 degrees centigrade. So we can make a graph of the difference between these two curves as a function of temperature. And this then gives us an idea of how well the persistent phosphor performs at a certain temperature. And this graph shows this. It's an even more complicated graph, because in red, we have the thermoluminescence, the total thermoluminescence intensity as a function of temperature without fading, so without waiting. So it's the total area of the curves in blue. And on the next slide, so here in blue, we see the total intensity of the TL curves here shown in orange. So the colors are not perfectly chosen, apologize. And the difference between these two curves gives us how much light is emitted during half an hour by persistent luminescence as a function of temperature. And so we see that at minus 60 degrees, as expected, this is very low. So there's hardly any persistent luminescence from strontium aluminate with europium and dysprosium at minus 60 degrees. But the ideal, let's say, working temperature of strontium aluminate, europium, dysprosium is at around 20 to 40 degrees centigrade, which is exactly room temperature. So strontium aluminate is really, really good for persistent luminescence at room temperature. It's less well suited for thermoluminescence at higher temperature. So this is the result of a lot of measurements on strontium aluminate, but the main result is that Strontium aluminate with europium and dysprosium is perfectly suited for thermoluminescence at room temperature. We also did this for different materials. This is the same kind of measurements for lanthanum aluminate with manganese 4+. This is an infrared emitter. And here we see if we do the experiment at 20 degrees centigrade, we hardly see any difference between these two curves, which means that there's no thermoluminescence or hardly any thermoluminescence at 20 degrees. It's better at 50 degrees, larger difference, 60 degrees, 70 degrees, 80 degrees. So here we really need a higher temperature to achieve persistent luminescence. So there's a bigger difference between these two curves, which also means that lanthanum aluminate with manganese is a good persistent phosphor, but not at room temperature. We really need this higher temperature. So we did a lot more experiments. We studied all these different compounds and made all the same experiments on these different compounds, and so try to find the optimum working temperature of these different materials. So they have different dopants, they have different hosts. So it's a whole series of different materials. And these were the results. So each time we can see the thermoluminescence measurements, the total intensity of thermoluminescence measurements as a function of temperature, the blue curves. Then after 30 minutes fading in orange, and the difference between the two in green. And there we can evaluate the optimum working temperature of these different phosphors. So for strontium aluminate, this is at about 20 degrees centigrade. For calcium sulfide with europium, this is a negative temperature. So here the optimum temperature is far below room temperature. For lanthanum aluminate, the example I showed on the previous slide, it's way higher than room temperature at around 90 degrees centigrade. So what is the main conclusion is that different persistent phosphors behave different at different temperatures because the trap depth is different for these different compounds. Now, there turns to be a very easy way to estimate the optimum working temperature of a persistent phosphor, because we can do this by just performing one single thermoluminescence measurement. And we look at the peak position of this thermoluminescence measurement, and we can see for these different compounds we tested. So here we have the maximum position of the thermoluminescence glow peak, and this is compared to the optimum afterglow temperature, and we calculated, we also measured the afterglow, and we can find a very nice linear relationship between the position of the TL glow peak and the optimum working temperature of a persistent phosphor. And the difference is about 20 degrees centigrade. So if we have a thermoluminescence peak of a material at, let's say, 50 degrees centigrade, then the optimum working temperature is at around 20 to 30 degrees centigrade. So this is a really fast way to estimate the ideal working temperature of a persistent phosphor. So summarizing for this part, we have, or we can make lots of afterglow measurements for trying to find out this perfect working temperature, or we can do this just by making a simple thermoluminescence glow curve, and there we can just subtract 20 to 30 degrees, and then we achieve the ideal working temperature. So this is a much more convenient way of working. Now, we also extended this work to more complicated trap structures because some materials have more than one thermoluminescence peak. But then again, it's possible to to estimate the ideal working temperature of a persistent phosphor. This is a paper which was just accepted in Laser and Photonics Reviews, so it should soon be available online if you are interested. Now, so we have a lot of persistent phosphors which can work at room temperature. So strontium aluminate is perfectly suited for persistent luminescence at room temperature. Some materials are not suited for persistent luminescence at room temperature, but maybe they are suited for other applications. For example, we have a very important application for persistent phosphors is bioimaging, where we would charge persistent phosphor and then inject it inside a mouse or inside a patient, and then look at the light emission as a function of time from inside the animal or the patient. Obviously, for vertebrates and for humans, the ideal working temperature of the phosphor should then be around 37 degrees centigrade, not at 20 degrees centigrade. So here we can choose materials which have an optimum working temperature at around 37 degrees centigrade. And it's perfectly feasible to try to find this kind of materials. We also looked for materials with a working temperature which is extremely low. And we found some chromium doped material. And here we again have the difference, the difference between a thermoluminescence measurement made without fading and with fading upon charging at -80 degrees centigrade. And so here, even at very low temperature, we could achieve light emission. Now, you could ask yourself, why would we be interested at afterglow at very, very low temperature, just such as -80 degrees centigrade? And here I can make the link with viruses because, so it's possible. So here we can see why the spectra are not so important, but in the left, we can see the afterglow at -80 degrees centigrade, which can be measured for a long time, for well over an hour. And here the application is as follows. Very often materials have to be preserved at very low temperature, such as, for example, viruses or biological samples. These are stored in liquid nitrogen. Now, if we attach to these materials, which have to be stored at very low temperature, if we attach to them a persistent phosphor, which emits at, let's say, -80 degrees centigrade, then we can check afterwards if the material has been stored for a very, very long time, maybe for weeks or for months or for years. We can check if the cold chain of this preserved sample has been broken or not, because if the temperature has increased from liquid nitrogen temperature to maybe -80 degrees centigrade, then the light of this persistent phosphor has escaped. If the temperature has remained low at liquid nitrogen temperature, then the light has not escaped. And so we can check in a very easy way, even after months and without using any additional energy, we can check whether for this deep frozen sample, the temperature has ever, during this period, been increased to over, let's say, -100 degrees centigrade. And so this can be a very important application for really checking the quality of the cryopreservation, so the preservation of materials at very low temperature. There's also materials which have very, very deep traps. And these very deep traps, for example, here we see a thermoluminescence measurement of a quartz sample. It's not my measurement, it's just took from literature, with a thermoluminescence glow peak at over 300 degrees centigrade. So here the energy will remain stored for an extremely long time, even for thousands of years. And this leads to very important applications, also both in dosimetry and in geological dating. For example, for personal dosimetry, materials are used which could be called persistent luminescent, but at room temperature, they are not persistent luminescence. They're called thermoluminescent dosimeters, TLDs. And here, it's the same kind of material, but just the traps are deeper. And if the traps are really deep, then the material can be charged by radioactive, by gamma rays, so by radiation. And if the sample has been charged with radiation, then light will be emitted from the traps when the material is heated to, let's say, 300 degrees centigrade, but not at room temperature. At room temperature, the energy remains stored, and so the radiation is, in fact, the radiation is not accumulated, but the energy in the traps is accumulated due to the radiation as a function of time. And so this is a perfect application for personal dosimetry, that materials can be used with deep traps for measuring personal safety. But these is, in fact, is the same kind of material as our normal persistent luminescent materials. The only difference is the depth of the traps. Also, some materials like quartz can also accumulate energy in traps. And these traps are really, really deep, which means that energy can be stored for thousands of years. And here, this can be used for geological dating, because if a particle is embedded in the soil, then light cannot reach it, but cosmic rays, high energy radiation, can reach the particles, and this high energy radiation can lead to storage of energy in traps, and this energy remains trapped for very, very long time. So this is exactly the same type of material as the persistent luminescent materials, but just with even more deeper traps. So here, this can be used for geological dating, because the amount of energy which has been stored is then proportional to the time that the particles have been embedded in the soil. So concluding, long afterglow persistent phosphors, well, the emission spectrum is obviously determined by the host and the type of dopants, but the afterglow time and afterglow intensity is determined by the traps. And then, very important, that the trap depth determines the ideal working temperature. This can be estimated from a single glow curve. And if the traps are very shallow, so then we can use this for cryopreservation. If we have a specific trap depth around 0.6, 0.7 electron volts, the materials are suitable for room temperature persistent luminescence. If they're a bit deeper, they can be used for bioimaging. If the traps are very deep, then we don't have emission at room temperature, we don't have fading, and we can use this for personal dosimetry. And if the traps are very, very deep, we can use this for luminescence dating in archaeology and geology. So this is more or less my story. It was a pleasure to be here again with you. And I thank you all for your attention. And I'm sure there might be questions. Can I stop sharing my screen? Yes.
Yes, sir. Thank you so much for your guidance and a speech regarding the traps in phosphorus. from virus prevention to geological dating. So it was awesome to see you once again in this gathering of the international webinar series. I hope the startup with your speech will make more successful to this program, sir. Thank you so much on behalf of Government VYT Autonomous College Durg as well as Bhila Institute of Technology Raipur. Thank you, sir. Our next speaker for the program is Professor KVR Murthy ji, MS University Baroda, and also the President of Luminance Society of India, for which I request Dr. Neha Dubey to give a brief description regarding him. Ma'am, please.
Okay, thank you, sir. Dr. KVR Murthy is professor in MS University Baroda, President of Luminescence Society of India. In recent years, a lot of research is going on the display and LED applications, and Luminescence Society of India play a vital role in this field. So many students completed their PhD with the help of LSI and under the able guidance of Dr. KVR Murthy. Professor Murthy has been completed his PhD from MS University Baroda in year 1990. He received Fellow Luminescence Society of India Award. He is the editor of International Journal of Luminescence and Application, edited 55 books on luminescence and application. He has guided 15 students PhD and 12 PhD is ongoing. Nearly 115 PhD examined by him, published more than 600 papers from various journals. He has been visited UK, Denmark, Italy, USA, China, France, Netherlands, Germany, Hong Kong, Poland, Singapore, etc. He has major research project of 50 lakhs, also working with the display industry for their research and development work. Topic of interest is photoluminescence, TL, thermoluminescence, LED phosphors, nanophosphor display application. And as far I know, Dr. KVR Murthy is very much energetic and very dynamic person and very much helpful person. Today's topic is COVID-19 pandemic and UV light uses and applications. So, Dr. KVR Murthy.
Thank you, Neha.
Morning, sir.
So, share screen. Yeah, can I start? Thank you very much to a brief introduction. I congratulate Jagjit Kaur for his kind consent and starting this first ever webinar from the YBT Government Science College. So basically it is a present scenario in the research is asked to discuss. However, but scenario is due to COVID-19 pandemic. So how we can use UVC radiations to control to disinfect the things. A brief lecture will be there, and what are the new devices for general application also discussed in this 30-minute lecture. Anyway, as a luminescence researcher, this is a basic electromagnetic spectrum where we work in the visible region. What are the materials we develop? And it may be whatever the luminescence phenomena that Dirac told. So from thermoluminescence to photoluminescence, so we'll work including electroluminescence. Especially UV rays, there are high energy UV rays are there, but we talk about only 200 to 280, where UVC we call, most of the UVC is blocked by the ozone layer, by the atmosphere. So the EV B and A also there. If you see the basic sizes and others, so 100 micron to few microns, our eye can see few microns also, up to 1 micron. Even combination of so many nanomaterials also, you can see nanopowder. But categorized bacteria, human head diameter, integrated circuits, microns, viruses. See that viruses. It is around 40 nanometer to 100 nanometer. So diameter of a atom is 1 nanometer. If we see size of the virus, say around 100 nanometer, how many atoms are there? So many molecules. So 0.1 nanometer, 1 atom. So it is approximately, you have 1,000 atoms, maybe few hundred molecules, maybe RNA or DNA in a virus. The light with a wavelength 10 to 400 nanometers is sunlight called ultraviolet, and it can be divided UVA, UVB, and UVC. Our interest is for disinfection and killing the viruses and the bacteria, that is 200 to 270 nanometers. If you see the solar radiation coming in the UV region, apart from others, so UVA, UV, UVC, you can see. Apart from that UV, other high energetic radiations are hard X-rays, gamma and hard gamma with a few tera electron volt to few electron volts in UV region. So basically, UVC ultraviolet destroy the DNA of a bacteria and viruses, and they play a role in disinfection and sterilization. Continuous low dose of far ultraviolet, that is far UVC, light can kill airborne flu viruses without harming human tissues, according to a study at the Center for the Radiological Research at Columbia University, Irving Medical Center, USA. From this, what we can understand is, so UVC source, if you keep somewhere in the corner at the center of the room, you can be away a few meters. So that may not affect humans much, but it can kill airborne viruses. The findings suggest that use of overhead for UVC light in hospitals, doctor offices, schools, airports, aeroplanes, and other public spaces could provide a powerful check on seasonal influence epidemics as well as influenza pandemics. UVC light can be cost-effective solution which eradicate the spread of virus. The main important is their UV light. So if you use so many sanitizers, their residues are there on the human skin or human body, including the environment. But UVC light, whenever the power cuts, so there are no high energy photons, even though they are there, that can be absorbed by the air within no seconds, maybe 0.1 millisecond, entire UV light photons will be absorbed by the gases like nitrogen, hydrogen, oxygen in the atmosphere, which includes H2 molecule. Ultraviolet light with wavelengths below about 290 nanometers germicidal, that is can kill germs, and it is sometimes used to sterilize medical instruments also. What are the medical instruments? Suppose doctors are treating some viruses affected patients. What are the equipment that are including stethoscopes, gloves, and others? So they can put in a UV chamber of 253.7 nanometer, which is mostly available in the market. So that can sterilize all medical instruments, including masks and dresses, what the doctors use. Interestingly, this application of this 253.7 nanometer UV light is used last 70 years for sterilization of the water. What are the UV filters are there, water purifiers. So first the water is passed through this 253.7 nanometers, which is having 5 electron volt energy.
आपने क्या कर रखा है? आपका काम तक दिख रहा है?
मेरा वीडियो देख रहा है उधर? अच्छा
नहीं, उधर से
नहीं तो हाँ स्टार्ट वीडियो।
विकास अदर माइक बंद करो, some other mics are coming. The wavelength that produce sunburn are around 300 nanometers, just at the edge of the solar spectrum. Solar UV light is also the major cause of skin cancer in humans. The skin cancer usually appears on the portions of the body that have received the most sunlight, such as tip of the nose, top of the ears, and the back of the neck. However, the disinfection lamp may not cause the above effect since the exposure time and intensity is very less. What it means is, once you put that light somewhere, so we are not going to be around. It is only hardly few seconds. We will be going away. We are avoiding. But when we work in the, especially sunlight exposing, so this long time exposures, long time exposures, not necessarily a day, is a number of days or number of years leads to this skin cancer. What it is means is, so UVC is a private technology for sterilization purification. So globalization and increased travel brings more attention to global public health. Many scientific research institutions and pharmaceutical enterprises are working hard on providing solutions for tackling such challenges. So today's pandemic, Corona, is such a situation. So almost a few thousand groups are working globally to tackle this Corona. UVC radiation is generated by high energy UVC lamps, moves to a wavelength between 280 to 200 to 280 nanometers, which is very versatile and can be used for disinfecting water, destroying harmful microorganisms in the liquids, on surfaces, on food products, and in air. With UVC technology, it is possible to destroy more than 99.9% of all pathogens within seconds, without addition of chemicals, without harmful side effects, and an inexpensive solution that is highly efficient and reliable. Why it is said is 253.7 nanometer photon having energy of 5 electron volts. Once so much photon flux is coming out, so in no time, so a few 100,000 photons are falling in a particular square centimeter, so which can kill any of the viruses, bacteria present on the particular surface. That is the reason it is very safe. Even food also, like food means your vegetables and bread and whatever prepared food also, just you can keep under a UV light for a few seconds, maybe 30 to 35 seconds is sufficient to kill the microorganisms on the liquids and surface of the food products. Coronavirus. Average human body contains more than 1,000 RNA proteins. More than 1,000 RNA proteins. But this coronavirus affects around 200 to 400 proteins in human body. But a healthy body, in all respects, the coronavirus is like your flu or common cold. Maybe you can take anti-inflammatory drugs, nothing but your paracetamol 650 mg for 3 to 4 tablets per day for a week. So it's supposed to be cured. But in certain cases, this virus is affecting the RNAs of 200, 400 proteins. Recently, 20 various types of coronavirus are found in Ahmedabad, India. So when I discussed with Yale Medical College about this type, they said there are 40 coronaviruses. Families are there. So this is taken from internet. So coronavirus are a group of related RNA viruses that cause disease in mammals and birds. In humans, these viruses cause respiratory tract infections that can range from the mild to lethal. Mild illness inside some cases of the common cold, which also caused by other viruses. while more lethal varieties can cause SARS, MERS, COVID-19. Symptom of other species vary. In chicken 1930, 1960, they cause an upper respiratory tract disease, while in cows and pigs they cause diarrhea. There also has yet to no vaccine or any antiviral drugs to prevent the treat the human coronavirus infection. Here, if you see, it was 1930. This first this coronavirus were found in chickens in Dakota, USA. In 1960, same coronavirus was affecting in Europe. They found they treated. But the present coronavirus, since already virologists globally, they indicated that 40 variety of viruses are there and they mutate. So today, different virus, same virus is infecting X and Y. But X may be treated very well, but Y may be fatal. Why is after going inside, how fast it is mutating. That means suppose an hour, 100 viruses can convert into million. In some body, 100 is equal to only 110. So your body can develop antibodies and take care of the these viruses. So when I discuss with so many virologists and doctors, especially scientists, nobody had any idea how fast the growth rate exponentially. Person to person is changing. Again, it is converting coronavirus 1, 2, 3, 4, etc. various types. So the subfamily is that in the family corona, Arachid and nidovirales and relem, riboviria. So there are the technical words. So they are enveloped viruses with a positive sense single stranded RNA genome under helical symmetry. The genome size of coronavirus ranges from approximately 26 to 32 kilobases, one of the largest among RNA viruses. They have characteristic club-shaped spikes that project from their surfaces, which in electron micrograph create an image reminiscent of the solar corona, from which this name derives. So we are converting the kilobars into nanometers. Coronavirus are large, roughly spherical particles with bulbous surface projections. The average diameter of virus particle is around 125 nanometers or 0.125 microns. The diameter of the envelope is 85 nanometer and spikes are 20 nanometer long. That means whatever the spikes are there, that can go up to 40 nanometer also. That is the reason maximum size is 125 nanometers. The envelope of the virus in electron micrograph appear as a distinct pair of electron dense shells. Whatever we are seeing, these are looks as electron dense cells. So the spike is around 20 to 40 nanometers. So total size of a virus is 1.125 microns. So 125 microns, 0.125, you can see a simple ordinary microscope shapes. You can see it's basically spherical shape. So if you see the sun, why this name has come corona? So we have the spikes all over the sun. Recently, last Sunday, we had this solar eclipse where you can see the corona type, ring type sun. To protect, what type of things what we need for corona is use of masks for protection. So it is mandatory or compulsory in India, in mostly global also. Use this mask and safe distance. Along with that, use a shield also. That is, it prevents more when compared to a simple mask. Shield is not required in the people are not around you. But people are around you, shield is compulsory, like police people and the doctors. Even though mask is there, shield is also a basic requirement. If you see applying the hierarchy, this is approved by so many international organizations. How best you can control COVID-19? most effective. Elimination, that means social isolation. You stay in your office with nobody is around, or stay at home with family. Any substitution is there? It said nil. How engineering controls can be helpful? So ventilation and physical barriers. So you have a barrier like a face mask, and you have a barrier of a glass window, and ventilation of the office space. It is always advisable not to use central air conditioning. Since this virus go to central air conditioning, again it comes into the air. So some administrative controls, what we are working now is work from home, staggering the schedules, hand hygiene, anyway, majority things we are observing. Least effective is gloves, masks, and PPE kits. They are least effective. Since the virus is hardly 100 nanometer, if it is somebody sneezes or something is there, the virus is around the air. So that is the best is elimination, social distancing, isolation. So that is the reason why all the government are insisting social isolation, and corona patients are treated in a separate wards. A simple microscope, how viruses looks, which is a magnification of 5,000 times. Electron microscope goes 10,000 to 50,000 times, so we can able to see what are the surface fine dust like that are there. They're around 5 to 6 nanometers we can able to see. So exactly how this UVC is working, you can see that. The cell nucleus of microorganisms contains, bacteria or virus contains thymine, a chemical element of the DNA RNA. This element absorbs UVC light at a specific wavelength. See, this 253.7 nanometer is the low pressure discharge tube, the mercury discharge tube, which is normally your compact fluorescent lamp as well as fluorescent lamp is available. But this UVC cannot penetrate through glass. So how best we can take out is using a quartz. So if you use a quartz tube, so whatever the low pressure discharge tube discharge is there, it will come out 253.7 nanometer, who is having approximately 5 electron volts. So this can penetrate the cell walls and the microorganisms and the viruses, instantaneously kills that particular. Why? If you give energy, it is basically assume that burning. You burn something, organic material, what happens? It burns away. Okay, like that. Once energy is given continuously, so all cells dies. That's all. A simple way. The high energy photon of the UVC are absorbed by the cell proteins and DNA, RNA. Energy approximately, if you take 254, it is 4.88 electron volts. UVC damages protein structure, causing metabolic disruption. DNA, RNA is chemically, so organism can no longer replicate. The basic thing is replication. That means multiplication. So once we kill, disturbs the RNA, DNA of the particular viruses or bacteria, so they cannot grow. When they cannot grow, there is no side effects. Because microorganisms are now unable to metabolize or replicate, the UVC light has effectively and safely sanitized the UVC workspace area also. That means if you put in a hospital or especially school or college, classrooms or hotel rooms, or improve our bedrooms also. So put on for 10 minutes and put off. That's all. You are sterilized. Any bacteria, especially coming is a winter. If a long winter, coming is a rainy season. Long rainy season is there 3 to 4 days. You always it is possible to grow microorganisms in the bedroom. We have one company in India, which is our limited collaborator also. So they are manufacturing some of the small sanitizer units. Maybe marketing within 2-3 days, they are going to market. This is the tripod mounted area sanitation system, which is useful for our colleges, schools, classrooms, as well bathrooms and teacher rooms, where a lot of human activity is there daily. This is tunnel sensitizer. That means if you want to put your mobile, and especially admission process, we require so many applications. Along with application enclosures are there. You can put that. So other side we can get a sanitized papers and sanitized anything you want, including vegetables. Here, 99.99% this COVID virus can be killed for different distances. This is theoretical scientific calculation using published technical papers and reports. 2 seconds to at 1 centimeter. Suppose your paper is there, so 1 centimeter is there. So once pass through it, within 2 seconds, it's sterilized. So 3 seconds, 3 centimeter. 12 seconds for a distance of 15 centimeter. For a room or classroom, we suggested 10 minutes. We put 10 minutes, put up and take that machine in the and put other room. This is handheld sanitizer. So suppose this can be lifted and put on your mobile phone, or somebody is giving something in the college. So instead of that, you can just sanitize using this handheld sanitizer UV tube. Yeah, this is the same developed physically by Professor Bisen and Professor Namita at Pandit Ravi Shankar Shukla University. This is on 28th June, a paper cutting from Raipur. So UV germicidal irradiation is well-known irradiation technology of all the technologies available. UV irradiation is superior as it is non-contact type. These equipment kill viruses types of all, including bacteria, fungus, that includes COVID-19. So any equipment, they have a product data sheet for details you can read. So wide range of applications, that is homes, offices, hospitals, shopping malls, banks, corporations and defense establishments for sanitation of against COVID and viruses. That includes aircraft. So if you aircraft you want to sanitize, you have to put some spray and others. So their aerosols will be in the air. So if you put this these equipment, 2-3 equipment in the 100 feet long aircraft, 10 minutes is sufficient to disinfect the entire aircraft. Thank you very much.
Thank you to Professor KVR Murthy ji. Thank you, sir, for your session on COVID-19 pandemic and UV light usage and its application. It was very good to hear you once again after the completion of the international conference. Thank you so much, sir. On behalf of Department of Physics, Government VYT Autonomous College Durg, as well as Billa Institute of Technology, Raipur. Thank you, sir.
Okay, thank you. Any questions are there, or just I have to stop share?
We are proceeding ahead for the upcoming speaker, sir.
Okay.
Thank you so much. The next speaker is Dr. Sudipta Som from National Taiwan University, IP. For the brief description regarding her, I would like to once again invite Dr. Neha Dubey to give a brief description about Dr. Sudipta Som. Ma'am, please.
Thank you, sir. Dr. Sudipta Som, he has been completed the PhD in the year 2014 ISSN pass. Postdoc fellow in South Africa from 2013 to 2014 under the guidance of Hendrik Swart. Working as a PDF from 2015 to till date, National Taiwan University, Taiwan. He has been published more than 75 articles with the citation of 1497. H index is 22. Recently edited a book with Dr. Vikas Dupe. The publication house of book is CRT Place, Taylor and Francis Group, New York. And the topic is luminescence material for the display and biomedical application. The topic of Dr. Sudipta Som is development of highly efficient and thermally stable phosphor for PC LEDs. So please, I'm requesting to Dr. Sudipta Som, please deliver your.
Thank you very much. Okay. A very good afternoon to all of you. It's my pleasure to be with you. I am thankful to the organizer of the International Webinar Series, especially to Dr. Vikas Dubey, for giving me an excellent opportunity to deliver a lecture on the revolution of solid-state lighting with low thermal quenching phosphor. Okay. My name is Sudipta Som. I am doing postdoctoral research at National Taiwan University. Currently, my research is focused on the development of micro-LEDs and design of related materials for high-resolution display devices. In the present slide, you can see the digital images of some of the micro-LED based displays taken from the internet. Last year, December, I had participated in an industrial meet at Taipei, Taiwan, with several of our industrial partners, including BenQ Computer, Edison Opto Corporation, Taiwan Textile Research Institute, for the discussion on the phosphor materials for LED fabrication. Though our phosphor quality was good in all other sense, the company personnel were worried about the stability, especially the thermal stability of the phosphors we are using. According to them, to date, the phosphors we are providing for LED fabrications or display application, maximum working temperature is limited to below 120 degrees centigrade to ensure the quality of the luminescence output. This is due to the deterioration of phosphors above the temperature 120 degrees centigrade. Hence, thermal management has become a significant issue as well as great challenge for the application of high-powered WLED applications. Therefore, today I will discuss about the thermal quenching related phenomena of phosphors and related applications. The title of my topic is Development of Highly Efficient and Thermally Stable Phosphor for Phosphor Converted LEDs. This is my agenda of today's talk. Before going into the main topic, I will articulate you about the place where I'm staying. Taiwan, an island country surrounded by Pacific Ocean, Taiwan Strait, and South China Sea. And National Taiwan University is situated at the northern part of the Taiwan in Taipei City. The QS global ranking of NTU is 66, and this is the aerial view of our university. With this unique fusion of culture, breathtaking scenery, diverse cuisine, exciting city life, and well-developed hospitality industry, Taiwan is an ideal destination for travelers and also for the researchers. Okay, now let's come to the main discussion. I'll start my discussion with the quote from Professor G. Blase, a pioneer of solid-state lighting. The modern society relies heavily on mankind's ability to produce light. Really, the first step of the advancement of human civilization is the knowledge of fire, that is the light. Light is a form of energy which can help us to see. Now, you just think how we can see any object. When light falls on an object and gets reflected, the reflected light helps us to see that object. Rod and cone cells in the retina of our eye can help us to see that object. I'm not going into the deep regarding the rod cell and cone cells for the time being. My next query is how we can see the color. Please don't think too much. Just think simply. As this photo says you can see this one, the white light is coming and we see a green surface, green leaf. We are seeing this as green because it is reflecting the green color and absorbing the all other colors from sunlight. Newton observed that color is not inherent in objects. Rather, the surface of an object reflects some color and absorbs all the other. We perceive only the reflected color. Thus, green is not in that leaf. The surface of the leaf is reflecting the wavelength, and we see this as green and absorbing all the rest color from the sunlight. An object appears to be white when it reflects all the wavelengths, and it observed to be as black when it absorbs all of the light. Now, if sunlight falls on an apple with leaf, just as this slide shows, we can see the red and green color respectively. No problem is there. Now, however, if red light will falls on that, only apple will show the red color and leaf is now black. If green color is used, apple will be black and the leaf will show the green color. And if blue light will be used, both will be, we can see as black. That means, I think you can understand my point. Like the fact indicate it is indicating that the white light is necessary to observe any object properly. Here comes our research. The main research of our main aim of our research is to obtain white light. Recently, there has been growing interest in high power phosphor converted white light LEDs, which are considered to be an alternative advanced lighting technology to conventional lighting devices, as shown in this slide. The search of light started from the starting of human civilization, as I told previously, that from the knowledge of fire, then kerosene lamp, then candle, to incandescent bulb, and the fluorescence lamp. All are to obtain the white light to see the object with artificial light. However, these light sources have intrinsic drawbacks, including cost effectiveness, global warming, toxicity, and etc. Then light emitting diode came into limelight. This is because of these three pioneers, Isamu Akasaki, Hiroshi Amano, and Suji Nakamura, who won Nobel Prize at 2014 for their discovery of efficient blue LEDs, which helps to obtain the excellent white light LEDs. The research on solid-state lighting was accelerated after this discovery. However, the LEDs are monochromatic and it can exhibit only single color, like say for example like blue, green, or red. But we need white light to observe any object. So one method is to obtain that white light is the multi-chip LED. We can use tricolor LEDs like blue, green, and red to obtain white color, as shown in this figure. And here you can see this design is from Professor Suji Nakamura. He had designed this one first for the white light generation with three tricolor emitting diodes: blue, green, and red. As the LEDs, you know that LEDs are narrowband emitter, means blue and red and green all are narrowband. That's why the color quality from this was not so good. I'll discuss the quality of the color, how we can decide that. I'll discuss this later on, like including color rendering index and color temperature. I'll discuss later on. The main thing is that the color quality we cannot get good with this tricolor multi-chip LEDs. Moreover, efficiencies of three LEDs will be different, and drive voltages for three different LED will be different. So the device design will be very complex. So that's why we have to change. This one to get white light some other way. Therefore, yellow phosphorus combined with blue LEDs draws research attention to obtain white light. 4 professors I have shown here. They from Japan. They are the forerunner for this kind of research. They have designed yellow phosphorus, namely you can heard about YAG, Y3Al5O12 cerium iron dope. They coat that kind of yellow phosphorus on the blue LED, and that yellow light, it combined with the blue light, it can provide the white emissions. As you can see from this photo, that blue and yellow color will give you the white light. The research of the light emitting materials, like known as luminescence materials or phosphors, has got an admirable beginning from this point. So So, however, the thermal quenching problem caused by the heat generated within LED chips result in a disappointing reliability and lifetimes of high-power phosphor converted LEDs, which is still a bottleneck limiting their practical development. To date, maximum working temperature, as I discussed previously, is limited to below 120 degrees centigrade to ensure the quality of the luminescence output due to the deterioration of the phosphorus above this temperature. Hence, thermal management has become a significant issue as well as a great challenge for the applications of high-powered LEDs. So before going into that one, we have to realize why thermal quenching is happening. I just want to share you this slide. You can see a structure of square planar complex here. The ligand can move from and to the central ion. This kind of figure I have taken from the book from Professor G. Blase, Luminescence Material and Applications. So now here you can calculate the force. You know Hooke's law. So force will be like F equal to minus kx, and from there you can calculate the energy is about half kx square. Now, if you want to plot the energy with displacement, you can get a parabola. Now Planck says, hold on, the energy is not continuous, rather discrete. The quantum mechanical solution of this problem, known as harmonic oscillator, is for the energy levels of the oscillator, and it is about E nu equal to nu plus half h nu, where nu equal to 0, 1, 2 like this, and you will be getting the vibrational level like this. So part of these levels are shown in this figure, and I'm just saying that for the time being, this is at the ground state. Now, if you give some energy to this system, what will happen? Here, if I give some energy, means what will happen to our this E versus X graph? If we give some energy, means our energy is now somewhat higher, showing by this red line, and when we'll be giving some energy, that means it will hamper the metal ligand distance. Means maybe the metal ligand distance will be higher or lower. I'm just I'm just taking in this case that it may shift towards our right in this graph. So just this line I can see. So this place will be for the my excited state. So this kind of diagram is generally called as configuration coordinate diagram. Now in optical absorption, the center is promoted from its ground state to the excited state. I'm not going into the details now. I'm just telling that electron that will return back to the lowest vibrational state of the excited state via non-radiative energy transfer first, then return back to the ground state by providing radiative emission. In ground state, it can go separate up to this level, and then from here it can non-radiatively decay down to the lowest vibrational level of this ground state via non-radiative energy transfer. Now, what will happen at high temperature? At high temperature, the initial state may not be this nu equal to 0. It should be nu greater than 0. So what if this level will be here? That means it merged with the excited state in that vibrational level. What will happen then? Then electron will return to its ground state by non-radiative energy transfer. That means it will quench our luminescence. This phenomena is known as the thermal quenching. We have to minimize this quenching for this research. Now, how we can minimize this one? We find that this cut point, this cross point of the excited state and ground state, the distance between this point and this point is generally called as the activation energy. So to make it less thermal quench phosphor, we have to increase this activation energy. Now, how we can do this one? Several researchers they have shown that, like if you can create some kind of traps that release the electron at high temperature. If you create some trap, previously it will trap some. If you create some deep level trap, it will absorb some electron previously. Now at higher temperature, it will increase, it will release those kind of electron to compensate that thermal quenching. So, but for this one, prior to go for the high temperature, the intensity will be somewhat lower. That means your efficiency will be less. So, and moreover, the control of the defects also will be complex. So rather, we can start with some hosts which are rigid to the thermal quenching. We can find some hosts with rigid bonding network, high bond strength, and then we can go for further research. Therefore, we have to choose new material with high structural rigidity. So this is the main motivation for our research recently. How can we choose this kind of phosphor? First, we have to discover the materials, followed by local structure analysis, and then we have to do material computation, and then we have to tailor the luminescence property, and finally we can incorporate this material for direct applications like LCDs, LEDs, and other different other applications. So first step for the discovery of new phosphor, for our case, we have chosen combinatorial search. Professor Sean et al. Developed this combinatorial approach to discover new material, and several researchers followed their work, and we also followed their work, and we can start our material discovery with this combinatorial approach. So what is this approach? So just for example, we are designing this we just first choose that primary elements, starting elements for this research. So say for example, in this research we have chosen SrCl2, SiO2, and SrO as our starting material. Now each and every combination we have tried with all the combination we have tried, and we have checked their PL and XRD. Some materials we didn't get the stable material like this way. Some materials XRDs are not pure phase, so we just cut out those kind of materials. We have chosen only those materials which are giving good PL and good XRDs. So means we have done this one. We have tried all this material with only Ce3+ and U2+ doping with the same concentration. Now we have chosen, thus we can get stable structures and record XRD patterns, and we can see the emission color for the further research. As I told, like next step is local structure analysis. So for the local structure analysis, we can use refinement. Here we have used PDXL software. You can use Topaz, FoolProp, and other different kinds of softwares are available. And then we have to evaluate the structure of the material first. Then we can evaluate the bond length distortion index and elongation factors from the refinement data as per the formula given here. If the elongation factor can be obtained near the ideal value for the perfect octahedron, it can indicate the high symmetry. And if the bond length distortion index will be large, then the 5d orbitals of the activator results in large splitting, which may cause a broadening in the emission. So the promising symmetric environment may lead to the highly efficient and stable phosphor. So by this structural analysis, we can optimize any phosphor material with highly rigid structure. What was our primary aim? Now again, from this one we can get how many sites are available for the rare earth to be substituted. For example, we have 3 sites available here, 3 strontium sites available here for U or Ce3+ to be substituted in that present rows. And we know that Nephrazeutic effect and crystal field splitting are the deciding factor for the emission color. So as we have 3 different kind of sites are available, so our emission color also will be different. Say for example, we can get 3 kinds of wavelengths from the similar phosphors. Those are expected to obtain. So after this local structure analysis, the next step is the material computation. So we generally follow density functional theory based calculations, which we generally perform by quantum exercise package. And the crystal structure of this material was simulated based on the experimental parameter, which we obtained from the refinement data. And in DFT calculations, we use generally the generalized gradient approximations and PVE type parameters as exchange correlation potential. Now, what we'll be getting from this DFT calculations? From this calculation, we can get the idea about the formation energy of each site and for the material, and along with the band distributions and band gap also. The formation energy is the indicator of the stable configuration. Now, if our formation energy will be very high, our material will be stable, like this way we can get. So whatever materials we have chosen, we have done the DFT, and from there we selected only the stable material for this study. And I think you can understand up to this one. So next step is tailoring the luminescence properties. So after doing this computational, we just use Van Wittert theory from our refinement data, and by conveying the specific coordination number into this present formula, the energy of the emission band could be estimated. Like previously, I have shown that we have 3 sites for the rare earth to be substituted, and we can estimate the value in each site. If you or she will be substituted in each site, value of the wavelength, how much wavelength it can provide. Then we can correlate the estimation with the probability of rare earth substitution evaluated from the DFT simulation, and we can tailor the luminescence properties with the variation of like synthesis parameter, compositional engineering, and rare earth concentration. In different way we can do this one. Finally, we have to choose the better material to be applicable for the devices. So like say for example, in the previous slide, I have shown a lot of materials we have chosen from the combinatorial approach. Now we have sieved some materials which are the better for the emission probability with high emission probabilities. Now we have to check the thermal stability of this phosphorus. So we have chosen I've shown here for the 2 phosphors here. The graph shows that the variation of wavelength and intensity with temperature. That graph indicated the decrease of PL emission intensity with the increase in temperature. However, the reduction in PL intensity, you can see from here, it is only about 10% at 180 degrees centigrade. I have shown here at 120 degrees centigrade, what we discussed with the company personnel, it is greater than 90%, which was their requirement. So those are comparatively high to the commercially available materials. And commercially available materials, some I have shown in this slide, some commercially available materials, their temperature dependent PL properties. And you can see that just only one kind of phosphorus, this has 0 thermal quenching, but for our case we didn't get that 0 thermal quenching, but we are getting very highly stable material. Moreover, we can use Arrhenius equation to calculate the activation energy from this formula, and that activation energy also will tell that tell about the thermal stability. In our case, we are getting about 0.35 or 0.31 electron volt, which is way larger than the commercially available phosphorus. So from here, we are now sieving out those materials which are thermally stable. So here I have shown some commercial available materials with different thermal stability, and another parameter for it also is associated with this thermal stability, that is Debye temperature. This Debye temperature we can calculate in both ways. One is DFT simulation, another we can calculate from the isotopic parameter what we have got from the Rietveld refinement. And from that one, if we'll get high Debye temperature, that indicates that high rigidity of the material, and high rigidity, it indicates the low thermal quenching. In our case, we are getting very high Debye temperature compared to the commercial one, and this indicates the low thermal quenching material for that. Okay, so up to this one, I think I completed all the parts. Now the last part is the application. So before going into that, we can discuss about 2 other parameters. One is color rendering index of the white light. I think you have seen, if you will be going to some trend platform, in that light, you can see your shirt color. Okay, you just see that same shirt color. You just come out for the daylight. You just see that shirt color. You can find obviously you can find some differences in both light. So herein I want to show a photograph also for a person wearing like blue kind of shirt in different kind of white light. You can see that that white light, the blue color, it pretends to be different in different kind of white light ambience. This is actually due to the sensitivity of our eye. This is called the color rendering. How our eye perceives a true color of any object is decided by a factor that is called the color rendering index. Color rendering index generally measured as a number between 0 to 100. The sunlight at noon, 12 o'clock, if you will see the cloudless sky, the color rendering index is 100. At 0 color rendering index, all the colors will be looking at, you can see that at same. And if CRI of 100, it shows the true color of the object. I have shown one apple. This is at in the white light with CRI 70. You just see, if I increase the CRI as 280, just the true color you can get for this apple. This is for the CRI 90, and this is for the CRI 100. So you can observe the true color at CRI 100. Another parameter I want to discuss, that is correlated color temperature. This is not the actual temperature of that specific color. It is the temperature of the black body which radiates this color. So, say for example, like if you just take a metal, if you heat it up, it starts glowing from red to yellow and then white. The temperature of that metal body is called that color correlated temperature. Not that this temperature is not that of the color. So, and herein I have shown different white light with different CCTs and different objects illuminated by various white light with different CCT. We require our CCT as per our requirements, such as if we require home ambience for reading purpose, we need white light near about 2700 to in between 2700 to 3500 Kelvin. And if we go for industry, for outside, we need bright white light near about 6500 or 5800 Kelvin CCT. So now we got an idea about the other parameters required for the white light. So now we will be going to the last part, that is the application. So we have designed LED with our phosphor. We have to design our LED with our phosphor, but prior to that, I'll tell about the commercial approach. As already I have mentioned previously, that yellow phosphors and blue LED it's shown here, but it is giving low CRI and high CCT values. This is due to the lack of red component in the spectrum, and hence other commercial approach to incorporate red and yellow phosphor with blue LEDs is available there. And more approaches are there that is recent, is incorporate red, green and blue phosphor with UV LEDs. Both the approaches exhibited CRI greater than 85 and CCT value we can control as per our own. But the approaches are like with complex synthesis approach. Some are prepared from hazardous material, and some used several color center. So instead, in our case, we are using only one kind of phosphor which can exhibit white light with highly thermal stability. So this is the electroluminescence spectra, and the same phosphor we have sent to company, and this is our we have designed this LED in our lab, and this is at company means Edison Opto Corporation. We have sent our material, and they have designed this kind of LEDs. And we got maximum CRI for this phosphor we have obtained as 82, and CCT ranging between 3500 to 5582 Kelvin. So I think for this kind of phosphors we are getting very good results, and this can be applicable directly for the direct appliances. Further, we have sent our material to CNRS France for flexible LED fabrications. we have means actually CNRS France, they have optimized flexible UV LEDs. Flexible UV LEDs they have done with molecular beam epitaxy. I'm not quite sure about their procedure, but they incorporated our materials to emit white light. And this is our most recent research. And you can see the for flexible display applications also we can use our material. And these materials can be applied in different applications. And I hope this discussion will be fruitful for future prospect. You can think about high thermal stability of the phosphorus. You can reach up to zero thermal quenching also for this prospect. And finally, I'll conclude again by saying the quote of Professor G. Blase: "The modern society relies heavily on mankind's ability to produce light." It was pleasure to be with you. I'm again thankful to the organizer of this international series, especially to Dr. Vikas Dubey. Thank you for your attention.
I request the panel members for any sort of queries regarding the session to be asked.
Okay.
Myself have a query regarding the implementation of this phosphorus, specifically in the LCD display, which is being displayed on the screen of the application.
Okay.
How will be indulged concept in the LED display screen?
Okay. Actually, you just want to know, like, for LCD display, how we can use our phosphor.
Exactly, sir.
Okay. So just first, for LCD display, we need a backlight. Backlight means that can emit white light. So in like in LCD, you have different cell color emitting pixel. They can emit blue, green, and red color. But for them, we need a backlight just to glow, for them to glow. So that backlight we can prepare with our phosphor.
Okay. So in the same fashion with respect to the street light as well as home lighting, the same
actually for the criteria is like for street light and home lighting, the criteria is different. But for display devices, again, the criteria will be different. Like for display devices, we need to get, I didn't discuss regarding that one, like we need to get high color purity. So that it can cover, like for CI diagram, for NTSC standard, we need to go greater than this NTSC standard.
So there might be a variation in terms of intensity also.
Yeah, intensity will be the first option, and then we have to go to the narrow band, and then we have to increase the color purity, so to get that display.
Yes, sir. Thank you, sir. Thank you.
Thank you.
I advise the remaining panel members to be asked for any sort of queries regarding the session what has been delivered by Dr. Sudipta Som.
Okay.
Ma'am,
thank you.
Sir, please.
Sir, one query from participant.
Okay. Okay, sir.
Sir, is there any way to improve thermal quenching?
Sorry, sir.
Is there any way to improve thermal quenching?
Yeah.
Question from your lab, sir.
Okay. So okay, there is lot of ways. Like first of all, like what I have told, like one way is that you can create some trap. You can deliberately create some trap. Like say for example, you have some host with Na like +1 valence. Okay. Now if you will dope some 2+ valence or 3+ valence, so you can deliberately incorporate some kind of defects, and we have to create deep level defects. So deep, what it will do, like when you will excite some with some light, the electrons will be trapped. Previously, electron will be trapped in that defect. At room temperature, it cannot come out. Now, when you'll be going to higher temperature, you know that at higher temperature, thermal quenching will be occurred, but that trapped electron, now it will compensate that thermal quenching phenomenon. So this is one way. Another way is that you have to choose the host as very rigid structure. Means the bond length and bond distortion index. You have to make it very packed, complete packed material, which we are trying now, just to find some material. And those kind of material you can find different methods, like data driven method and like combinatorial approach and solid solution techniques. Different methods you can find, and you have to design lot of phosphors, and out of that one you can choose what will be your most rigid structure, and what is giving you the more high intensity.
Thank you, sir.
Oh, thank you, sir.
Hello.
Yes, sir.
Good afternoon to all, sir.
Thank you, sir. Good afternoon.
This is the question at the common platform. Since we are discussing about luminescence and its various criteria.
Yes, sir.
I am working in the field of crack detection in cementitious material.
Okay, sir.
Using different dosing, using tropium, dysprosium.
Okay, sir.
But due to in absence of exact or definite molecular formula of cement, I am unable to mix the exact proportion.
Okay, sir.
Please suggest, sir.
So, whatever I got your question, like you want to know exact structure of that cement. Sorry,
exact
sir?
Exact molecular formula of cement.
Okay. Okay, so for this one, first you have to simulate the structure. So the cement, I think it will be giving amorphous peak in XRD, or it will be giving the crystalline peak. It is giving
semi-crystalline peak.
Semi-crystalline peak. Okay. So for semi-crystalline peak also, I think we can try for that refinement. So first we'll be going for refinement, and cement, I think silicon will be there. So we have to choose some crystallographic information file, and from there we have to just refine our structure. If we will be successful with that refinement, then we can tell the exact formula for this, how many sites are available and what are there in this one. So maybe I have to check that XRD file, then I can tell you. I think I can request Dr. Vikas Dubey to give my email ID to you. So I think we can discuss regarding this one.
Okay, sir.
Yes, sir.
Thank you.
Thank you, sir.
Thank you so much, Dr. Sudipta Som.
Oh, thank you.
We're having a session on the topic development of highly efficient and thermal stable phosphorus for PC and LEDs. Thank you so much for the session, sir. Now I would like to request Dr. Jagjit Kaur Saluja ma'am. Please, I would like to invite you for concluding today's session overall. Ma'am, please.
Very good afternoon to all of you. Today is on this webinar, international webinar on worldwide effect of COVID on research and development. I am going to conclude this. Before concluding, I welcome all the participants and our eminent speaker, Professor Dirk, Professor KVR Murthy, and Professor Sudipto Som. I am very much thankful to all the speakers and all the participants here. Today we started the inaugural session with the welcome address by Principal BIT Raipur, Dr. Ramarao. Our first session started with our eminent speaker, Professor Dirk Poelman of Ghent University, Belgium. His lecture was on traps in phosphorus from virus, preservative to luminescence dosimetry. He explained how to enhance the persistence luminescence using different colors and different dopants. He also explained in his lecture in detail how persistent luminescence occurs and how luminescence centers occurs with the emission colors, etc. And how we can get the brighter and persistent luminescent phosphors. He also explained the persistence luminescence is highly temperature dependent, and the afterglow measurements and how long the decay and how low the decay. He also discussed the TL measurements, TL experimental procedures, and he also discussed that strontium aluminate is very good persistent luminescent material with dysprosium and europium. Dr. Dirk also explained the application of phosphorus, persistence phosphorus for bioimaging, geological dating, and then he concluded his lecture. Our second lecture was by Dr. KVR Murthy, Professor, MS University, Baroda, Gujarat. His topic was very recent topic and very knowledgeable, informative topic, that is COVID-19 pandemic and UV light usage and applications. He explained about the ultraviolet light, UV rays, and their effects on skin. He also discussed how the UV rays destroy the bacteria and viruses, and the role of disinfection and sterilization, and how we can use the UV light for this sterilization, and how UV light can be used for medical instruments and to sterilize the instruments. He explained how the UV proven technology, sterilization and purification. He covered his lecture by giving information about the coronavirus effects, RNA 200 to 400 proteins in human body, and also throw light on the size of coronavirus and how to protect ourselves from corona. He discussed that to prevent the corona, we have to work from our home and we have to maintain the social distancing. The importance of UV rays and how UV can destroy most of the microorganisms from different institutes like schools, colleges, hospitals, and other malls, etc. He suggested the time of exposure to kill COVID-19. He also demonstrated one equipment for COVID-19 by UV and explained the wide range of applications for home offices and different institutions. Our third eminent speaker, Dr. Sudipta Som from National Taiwan University, Taiwan. His lecture on the topic, development of highly efficient and thermal stable phosphors for PC LEDs. He explained color quality and history of light emitting diodes. He started how we can see the objects and observing their colors. What is the use of white light and why white light is necessary for any object to detect colors. He explained LEDs, generation of white light and multi-chip LED. He also explained quality of white light and thermal quenching. He covered the area how can we choose phosphors which are cost effective as well as white light emitting phosphors, and how we can select the host materials and good white light diodes. He also explains the thermally stable materials and discussed about the quality of white light, CRI and CCT, and concluded his lecture by giving the application of single host white light emitting phosphors. And after that, question answer session was started, and some of the questions and queries from participants as well as from speakers. I am concluding today's webinar by giving my vote of thanks. I am very much thankful to our eminent speakers of today's webinar, especially Professor Dirk from Belgium, Professor KVR Murthy from Baroda, Professor Sudipta Som from Taiwan, for giving their valuable time and sharing their views with us. I am very much thankful to all the participants from all over the country. I am very much thankful to organizing committee. I am very much thankful to the Principal BIT Raipur, Principal Government VYT PG Autonomous College Durg, Department of Physics of BIT Raipur, and Department of Physics of VYT College Durg. I am very much thankful to all who are giving their support and participate in this webinar. Thanks to one and all. Thank you very much. Thank you, sir.
Thank you so much, ma'am. You as a convener for this program has been initiated successfully. A heartiest congratulations on behalf of the whole team who has been taken a part in this event. And all the participants, for the kind information, tomorrow's session will start from 5:30 p.m. onwards. We have speakers from New Jersey as well as Poland. With your kind interest and with same enthusiasm, we would like to expect to see you all on tomorrow's session. Thank you one and all. Thank you to the speakers who has been participated today. Thank you, ma'am.
Thank you, sir. Thank you, Doug, sir. Mute है क्या? उनका mute है. Thank you, sir. How are you, sir?
I'm fine, thank you.
Thank you, sir.
Thank you very much.
Thank you. Thank you, sir, for your valuable time, sir.
Thank you.
I am very thankful to you, sir.
Bye-bye.
Bye, sir. नहीं अभी बंद नहीं करना, बोल रहा था कि ऑफ नहीं करना है ना उसको. मीटिंग को एंड कर दे.